going on in your class. By the way, this is the first sentence that the stream caught, so it's out of context. Limits at infinity. I'll have to trim this video. Yeah, so infinite limits and then limits at infinity. So infinite limits is where the answer is infinity. Limits at infinity is where you are sending x to approach infinity, either positive infinity or negative infinity. So we are dealing with this situation now. Limit x goes to either positive or negative infinity of a function, and we are looking for a finite value of some sort. Now, you still can get infinity there as well, and this section will define two of those pre-calculus concepts that you learned. One is horizontal asymptote, and the other one is the end behavior of functions. So both of those were studied in chapter 2, if you use the RVCC chili pepper book. And we cover those in 2.6 when we talk about rational functions. So now let's take a look at these limits. I can still use good old 1 over x because it does also have these kind of limits. So let's see. We have a limit of, let's say, 1 over x as x goes to positive infinity is equal to what? Zero. Now observe that these limits are always one-sided, technically, because you can approach infinity only from one end. Does that make sense? Good. So positive infinity is this way. As you are approaching positive infinity, you see that the y value, which is what limits compute, the y values, y value drops down to 0 elevation, right? So these are the y's. So y keeps dropping down, and as x goes to infinity, the y value goes to 0. And believe it or not, we're done, right? That's the theoretical part behind it. Now we're just going to say and wrap this into horizontal asymptotes and the end behavior of functions. So let's start with the horizontal asymptotes. So horizontal asymptotes occur when a limit as x goes to either positive or negative infinity of the function is the finite value. And I'll point here and say finite value. And the example of that is right above. So there is a horizontal asymptote there, because as you can see, when it goes to positive infinity, it drops down to 0. 0 is a finite value, therefore horizontal asymptote is at 0. So we are going to say like this, and we'll say horizontal asymptote at y equals 0. Again, very important to use proper notation for lines. We have, for vertical lines, x equals a number, and for horizontal lines, y equals a number. So those are the ones that we have. Okay, we have that as the idea. Now, in your pre-calculus course, you did memorize, since you passed the course, and then possibly forgot, the 3 rules for horizontal asymptotes if the exponent on the top is larger, if they're the same, and right? So you can now forget that if you haven't already, because we are going to solve the limit for it, and we will know how to deal with these limits. It's important to have this observed at all times, that if you divide a number by a variable that goes to infinity, you get 0, and that's our experiment with the paper. So if you keep that in mind at all times, the rest of the problem is going to be fairly simple. So let's deal with polynomials first. We have the limit, let's say x goes to positive infinity, of x squared minus 3 divided by 4x squared plus 1. Now you know how to deal with this. with pre-calculus. What was the rule when the exponents are the same? Does anyone remember? Yeah, you divide something, exactly. Constant? Yes, divide the front constants. Very good. So the answer is 1/4. If you memorized that rule from your pre-calculus course, cx squared is the leading term, and then 4x squared is a leading term. They have the same exponent 2. So the front coefficients 1 and 4 will be the ones for the horizontal asymptote. So horizontal asymptote at y equals 1/4. But now we can actually do the limit, so that knowledge is no longer required. Now, if you still know it and if you relearn it now, doing this problem is going to be much faster. But we can still do this algebraically. So the way you do this is you divide every term inside by the highest exponent in the problem overall. So the highest exponent in the problem is x squared, so we have x squared divided by x squared minus 3 divided by x squared, 4x squared divided by x squared plus 1 divided by x squared. You cancel all the x squares that you can, and what you get is the limit x goes to infinity of 1 minus 3 over x squared divided by 4 plus 1 over x squared. And by this rule here, where the 1 or any kind of number, like I can keep ripping 3 papers or 5 papers or 10 papers apart forever, they will still go to 0. So when you start ripping them to infinity, you get 0 on the other end. That means that all of these terms with x squares, they immediately go to 0. And the limit of 1/4 is just 1/4, right? Because we know the rule, limit of a constant is that constant. So we will say horizontal asymptote at y equals to 1/4 because the limit was 1/4. Let's take a look. I just want to see if the stream is working, and it is. Good. So now let's take a look at more examples of this. So let's pick something from homework. They're all the same. You can solve one of these. Let's go with problem 30 because we can. So x goes to infinity. We are looking for horizontal asymptotes of this function. X to the 4th plus 7 divided by x to the 5 plus x squared minus x. So what's the highest exponent for the whole problem? X to the 5th. Very good. Divide everywhere by x to the 5th. Cancel everything you can. Assign zeros for all of those with x in the denominator. the answer? 0? All good with 0? So let's take a look. So we all agreed that the highest exponent is 5, which means that we divide each one of these terms by x to the 5. Don't forget to copy the limit every time until you get to use it. So we have x to the 4 divided by x to the 5 plus 7 divided by x to the 5, and then x to the 5 divided by x to the 5 plus x squared divided by x to the 5 minus x divided by x to the 5. Now we cancel. Limit x goes to infinity. When we cancel the ones on top, we get 1 over x plus 7 over x to the 5 stays as is. On the bottom, we get 1 plus 1 over x cubed, and then minus 1 over x to the 4th. Each one that has x in the denominator will go to 0, because as I divide 1 by infinity, I get 0, which is I rip one paper infinitely many times, or I rip 7 papers infinitely many times, I still get 0. So all of these go to 0. And what I'm left with is the limit of 0 over 1. As x goes to infinity, just 0 over 1, which is 0. And that's it. Problem solved. So what is the importance of these? We'll talk about the application. Let's first take care of the end behavior of functions. So function can be graphed, and the lines extend to the left and to the right. And if they are not finite, if they're infinite, they will go to one of the infinities, either positive or negative. Now they can be constant, or they can go to positive or negative infinity. So to understand the end behavior, I mean, you did this in pre-calculus, so you should know what it is. You look at it this way, let's say for x squared, y equal x squared, and the end behavior is talking about these two behaviors here. So you see that this behavior is explained as limit x goes to infinity of x squared is positive infinity. So this is the mathematical notation which explains that particular behavior. On the other side, we would have a limit of x going to negative infinity of x squared is going to positive infinity again, because the answer is showing what the y values do, and the x goes to either positive or negative infinity. So what we have on the other side is the limit x goes to negative infinity of x squared is equal to, again, positive infinity for y's, because it goes up. Let's take a look at the, let's say, cubic function. Let's have some of the more interesting cubic function like this. And then, again, the end behavior are these two parts. So this one is still the same. Limit x goes to positive infinity, because we're going to the right, of whatever the function it is, it doesn't matter, is positive infinity. The one on the bottom is limit x goes to negative infinity of x squared is equal to negative infinity now, because it goes down. So the end behavior of these functions is captured in those essentially 4 combinations, where x goes to either positive or negative infinity, getting positive or negative answer. So to kind of summarize all of this, you can just have a chart, and then in this chart you have something that goes like this, like this, and like this. Those are the 4 possible ways. Obviously, if it's constant, it's going to be horizontal asymptote if it's a constant, because the limit goes to infinity of, and you get this finite number, you get horizontal asymptotes. So this one is limit x goes to positive infinity of f of x to get positive infinity, and then limit x goes to positive infinity of f of x to give us negative infinity because it is going down. Limit x goes to negative infinity, f of x gives us positive infinity, and finally limit x goes to negative infinity, f of x to give us negative infinity, and that is it. So, very interesting function to look at as an example of this would be f of x equals, let's say, e to the x. So what is the end behavior of e to the x? I'm sorry, what do you mean positive? Yeah, I'm asking for the end behavior, but it has 2 ends, yes. Yes, she said. Which is? Which is, you get 0, which is? Horizontal asymptote. Very good. So end behavior, in this case, on one end we get positive infinity leading into positive infinity. On the other end, it leads to 0, which is at the same time horizontal asymptote. So we're going to, we all know how exponential function looks like. Looks like this. So end behavior, on this side we say that the limit as x goes to infinity of e to the x is positive infinity, and on the other side the limit as x goes to negative infinity of e to the x is 0, which is horizontal asymptote at y equals 0. Excellent. Now the end behavior of functions is very important, and if you have a good differential equations course, your professor, yes? That was real quick. I know. You're welcome, free of charge. So end behavior plays a large role in differential equations. As I said, if you have a good course that has application of differential equations, you would look for the end behavior of the answers. So in differential equations course, you solve equations that have functions as solutions. And those functions you can send to infinity to see what is happening with that solution as usually time goes to infinity. So not to go into details of solving any of this stuff or so on, you might recall from your pre-calculus course that the population in respect to time is equal to initial population, which is the P naught, initial population. I remember the question at the beginning of the class. E to the kt, where so P0, P naught is the initial population, and then K is the constant of population change, whether positive or negative, and then T is time, usually in years. So, but it could be also in minutes or hours, depending whether you're talking about virus, bacteria, whatever else. So now looking at this particular population model, you see that this is not viable to use on a long run for human population on Earth, because just for one reason, and that reason is that the end behavior of this function is as t goes to positive infinity, the population will go to positive infinity. And we know that that's not possible on the planet that has a finite surface area, finite resources in terms of energy, food, and everything else. So our planet has the carrying capacity. So a different kind of a model, more of a, let's say, logistics model, would be more suitable to talk about population of humans, because you really cannot reach the infinite population as this mathematical model would suggest. Now, this is good for short-term calculations, but it's not good for long-term ones. So if you go and you take a look at the limit of p0 e to the kt as t goes to infinity, which is end behavior, you will get infinity on this end, because the graph looks like this. This is your p0, initial population. This is the time axis, this is the population axis, and this is where the time is 0. So at time equals 0, that's the beginning of time, right? So we have whatever population where we start measuring, and then the population would grow. So this particular model is not as great. Now, as I said, there are other models out there. One of them is the logistics model. Depending on which numbers and values are used, let's go with A is equal to A over 1 plus B e to the minus kt. Now, this is a logistics model, and this logistics model will have a graph that looks like this. And you see that so let's say that's the population and that's the time. So now you see that this particular one has a horizontal asymptote at some value which we call carrying capacity of the planet. So now, depending on the research and factors that are taken in to calculate how many people planet can sustain, we can see that regarding some calculations we are well over 50% of population that we can sustain, but then there are some there as low as 10 billion. Some are 15.2 billion is the largest one I heard of in terms of carrying capacity. So we are at 7.4 billion. That's about half if you look at the largest. Now, what does it mean having the population at its carrying capacity?
Well, that would mean that if many more people are born, then there will not be enough resources for everyone.
Yes, there will not be enough resources for everyone. Yeah, technically, essentially. So all of these issues, and we are already experiencing these problems in terms of pollution and global warming and everything else. So there's a lot of environmental concerns regarding these kind of concepts. So as you are learning about the end behavior of functions and so on, this is one of the applications that comes up.
Never mind.
Disregard?
Yeah.
No. As you wish. So I would like to bring up one more application of this, and then we'll take a look at those graphs. So we covered so far two different types of these limits. We have limits at infinity and infinite limits. So infinite limits were the vertical asymptote, where the limit as x goes to a finite value of f of x from either side, plus or minus, needs to be positive or negative infinity in order for us to have a vertical asymptote. And then we had the horizontal asymptote, which is the limit needs to go to positive or negative infinity of f of x to be a finite value to give us the horizontal asymptote. Now we also had from here the end behavior of functions looking at the infinite rise or infinite fall. Now what we are going to do here is also look at the application and see what's happening. Can you find any physical ramifications of all of this, even in a classroom? And the answer is yes. We're going to take a look at the outlet. All right, the outlet where you plug in your cell phone chargers and other devices in the house. Did anyone of you ever experience a short? And what happens? What happens if you short the two terminals on the outlet? What happens? No, you don't have to shock. Not necessarily. Everything connected to it turns off, but is there a little explosion there? A little poof, right? There is a little poof. So now let's talk about explosions, because we can. Yeah. Yay. So Ohm's law. In physics says that the current is equal to the voltage divided by resistance. And so the current is the electron movement through the wire. The voltage is the difference of potentials between the two terminals, which allows for that flow. You can always connect the electricity to a flow of water through a pipe. So technically, if I put some water into a pipe that is horizontal, whose potential on both ends is the same, remember the potential energy means that one end is higher than the other. So if there is no potential difference in terms of the height for the two ends, the pipe, the water inside would just be stationary. It would not flow. So the same like, you know, a swamp or a lake, the water just stays there because it's just flat, where if there is a stream or there is a river, it always goes downhill. So you will not find a river that goes uphill. So if you create a difference of potential, then the water will flow through the pipe. Now the electricity, this is analogous to what's happening in electricity. You have electrons that are moving due to the difference of potential inside the two prongs that you have where you plug in stuff. So now the current is the motion of those electrons, the voltage is the difference of potential, and the resistance is the one that is inside the coil. For, let's say, a cell phone charger, it has that coil inside that transforms 110 into 12, so that has resistance. Now usually what you do is, if you look at the cell phone charger, it might say 1 amp. Now that means that if you have 110 volts in the outlet, there is the 110 ohms of a resistance to produce 1 amp of current, and then that is transformed down into 12 volts with the power and so on, so it charges your cell phone. We are not going to go into any of that stuff. What I'm interested in here are these limits that we just learned, because I want you to see that what you are learning now, starting from calculus, is exactly what you are going to experience when you start working as engineers, researchers, or whatever you are going for, because otherwise you will not be taking calculus, or would you? It's actually, yeah, intellectual curiosity, right? Any film directors? No? Because I took differential equations with the film director. He was going for that major, and he was taking calculus 1, 2, 3, and differential equations. I asked why. And he said, And the going joke would be that every time he does casting for any of his movies, it will be, you can't solve this differential equation, you can't play in my movie. I said, dude, you will never make a movie. And I don't remember his name, so I have no clue whatever happened with that. But it will be a good story. Anyway. Well, actually, no, I could star in that movie. Yeah. Slav Superstar, right here. All right. Let's go and talk about this. So what would happen here? If you short something, that means that the resistance is 0. And here is your limit at work. You have a constant 110 volts, which is divided by 0. And in our limits, what's happening as denominator is 0? Current is going where? To infinity. Now, there is also a formula in physics. I won't bother you with it, but I will tell you that it exists. A formula that says that current is proportional to a temperature. The more current you have, the higher the temperature. So you know that your cell phone charger gets hot. right? And all of the stuff that you plug in, they have this work temperature. Well, that temperature is produced by the motion of electrons. Motion of electrons is any type of heat is just coming from the kinetic energy of moving particles, moving things. So you have motion of electrons because a lot of current is trying to go to infinity. That means that the temperature is trying to go to infinity, right? Now that's why we have the circuit breakers, because we don't want temperature to go to infinity, right? And it's that temperature that causes electrical fires, right, for houses and so on. So you shouldn't be swapping your 15 amp fuse with 20 amp fuses because you haven't upgraded your wiring in the house. So that's why licensed electricians are important, and that's why they make so much money. Because if you constantly plugging in stuff into your outlets and your breaker is popping, that means that you are putting way too much load on the circuit that you have in your house. Now, some people would just go and swap the fuse from 15 to 20 without swapping the wiring, which is still rated for 15, and they keep plugging things in, which heats the wires too much. And now, what are our houses are all wood and cardboard. So, right, of course, it's going to burn down. So don't mess with it, right? But here is the example of our limits, and here are the examples of that going to infinity. We are only looking at one part of this. So this and this one, this will be your current, and this will be the resistance. And as you can see, as the resistance goes to 0, meaning you are shorting it, the current goes to infinity. If the current goes to infinity, temperature goes to infinity, hence fire. That is the reason why you see a little explosion as soon as you short the outlet. Now, obviously, the circuit breaker will kick out, and then there will be no further electricity to actually, for you to continue doing that, you will have to reset and then try it again. So that's one of the applications. It is extremely important to catch these kind of things as you are designing electrical circuits or whatever else. And for this particular reason, and now you see this is the explanation of why it happens the way it happens. So that would be the application, a little bit of what this stuff is good for. And now we're going to take a look at those graphs. Do you need another break? Nah, you're going to power through and we're going to finish 5 minutes early. How about that? So we saw different ways to find limits. The one that works 100% of the time is the table of values. Because depending on how complicated function is, graph might not be available if you don't have a graphing calculator or Mathematica with you. And not every problem can be done algebraically, which was 2.3. So the only method that works 100% of the time, but it's by far the most annoying of all, is the chart of values. You will choose the values smaller than the number you are approaching, compute all the y values, and look at the trend. Or you will look at the values that are higher than the value you want to approach and compute y values and look at the trend. So that works in 100% of the examples. We would prefer to draw a graph. If we can make quick conclusions looking at the graph, that's awesome, right? But as I said, sometimes the graph could be complicated. And the third method is to compute it using algebra. And we saw technically 3 methods. The first one was just plug the number in. So if we don't have 0 in the denominator, if we don't have anything weird happening, we can just plug in the number, the value, and we will come up with something on the other end, whether it's finite or not. If that is not available, well, in that case, maybe we can factor, maybe we can rationalize, maybe we can cancel things. So the bag of those tricks is finite. Technically, those 3 are there, and you saw all of them at work. Now, what are the interesting questions that we could answer? We said that the limits are the fancy way to compute function values, but they also do more than that. Now let's just draw a function. Try to get this as close as possible to what I have. So I'm going to do a piece like this and open circle here. I'm going to close the circle there, do the maybe a linear piece up to here. Then we can, so linear piece is a straight line, right? Then we can maybe drop open circle here and go forever down. There we go, perfect. That's good enough. And now I'm going to put a dot right there. Now something like this you get to draw, you get to explain through piecewise functions. Now I really don't care what the formula for this is, because I have graph and I can find all of the limits that I want. And I'm interested in particularly in three limits. I want to take a look at the limit as x approaches, this is -3 of this function. I also want to discuss the limit as x approaches 0 of this function, and the limit x approaches to 2 of this function. And they will all give us some insight into the relationship between graphs and limits and all of these things, pre-calculus 1 and calculus 1 and so on. So let's first discuss x equals -3. So what would you say that's the limit as x approaches -3? Doesn't exist. Why would you claim that?
Because, well, we're proving from the left and we're supposed to differentiate
2, okay.
and the right is approaches 0.
Very good. So I'm just going to say, because limit x approaches -3 from the left, which is -3 minus, is going to, of the function, is going to be +2, and the limit x approaches -3 plus from the right, f of x is 0. They do not agree, so by that important theorem from last class, left limit, right limit do not agree, therefore there is no limit. Now how about x goes to 0? 3. Limit is 3. Left limit goes to 3, right limit goes to 3, and we are good. Now how about number 2? X approaches 2. What is the limit? 2. Nice. The limit is 2, because both left and right limits are approaching value 2. Now what is the value of the function? What is f of 2? 4. Good. F of 2 is 4, because that's where the value is. So we have to distinguish between the computation. I said that the limits are a fancy way to compute function values, but then they work not on the single points, they work on intervals, because we have to have a line segment of some sort. We have to have a neighborhood of the point that we are approaching so that we can compute limit. Remember, limit never computes the value you are approaching. Limit computes all of the values around it and then infers where the x should go, where the y for that x should be. Does it make sense? That's it. Sounds good? All right. Well, that will be it for this lecture. Now let's go and print and do some labs, because we have we have 2 minutes left and then another 25 after that. So how about jump into some labs? That's it for the stream. We'll continue tomorrow.